Welcome to the Decarbonization of Cement panel. I think it's going to be a very fascinating hour and a half, 2 hours. We have a few very insightful speakers here today with us. Let me, before going into any detail, introduce our speakers to the room. We have Dr. Lukas Gast. He is on the forefront of researching and working on how we can actually decarbonize the industry, not just the cement industry, through novel technologies, making them affordable, and using basically innovation to drive the whole thing forward. We have with us Carolin Boßmeyer. Thank you for taking the time from your work with Heidelberg Cement. Carolin heads the liaison office here in Berlin for Heidelberg Materials. Of course, yeah, I still need to, it keeps coming in, right? But I think that already points to part of the solution. We're not just talking about cement, but materials henceforward. Carolin has a background with the construction industry, but also with biodiversity. I saw you were managing director of a biodiversity NGO for many years, so it's glad to see that broad background. And I think you also had a stand with Joschka Fischer and friends.
Sure.
Yeah, so that's
long time ago.
A long, a wide range. And then Professor Dr. Volker Thome from Fraunhofer in Stuttgart. Almost. That's why. Okay, so many different research places. He heads the Department of Inorganic Materials and Recycling, really at the Fraunhofer Institute for Building Physics. So that's, we're right in the depth of the cement mixer, I want to say. And I think you've seen many materials, and so we look forward to hearing, what's new on the R&D front. What can we learn from? I saw all the way back to the Romans. So there's a lot. A novel technology, but also ancient technology that maybe is part of the solution for today's panel. Now, before we jump in, we're going to have a few short keynotes and then have a discussion as in the previous panel. I wanted to set a little bit the stage. What do we actually want to discuss here? Because we're not, I mean, it's brick and mortar, I guess, but what is it actually we're trying to achieve? I think the lead question is, how do we get to net zero in building materials, in particular in cement? And perhaps we should even ask the question, can that be achieved? Can we create building materials without any emissions in the future of buildings? So that's a science question, but it's very much also a market question and a cost question. And I think some of the questions we'll touch upon today is whether actually cement is a hard-to-abate industry, which technologies are already available to get us to net zero in cement and construction. How do those new materials compare to what we call Portland cement, right? So the classic cement that is used in every building that we know. Where do we need to do more R&D and innovation? So where are we lagging behind in terms of getting to net zero building materials? And also, questions on the market in terms of innovation, climate tech startups, advancing material science, and so forth. But I think it all comes down not just to a material question, but really also to a business question. And I think that's also why it's such a good space to discuss this here in this, between the regulatory, the business, and the material science. So how can we afford all of that? How much is all of this going to cost? And what can we actually do to keep an eye on the price point, on the cost of each bag or ton of building material that comes out of it? I think that's, in the end of the day, so how can we use innovation to push down the price point for these green building materials so that eventually they even become cheaper than ordinary Portland cement? I think that's really, the guiding, the high level question we have. Now, before jumping in, I wanted to ask a question to the room. So Portland cement is what you'll get in pretty much every construction site. Sometimes people say that historically the building industry has been one of the industries with the lowest levels of innovation and R&D in the past. I'm not sure if that's true given how much research centers exist. But I wanted to ask you this Portland cement, how old do you think it is? When was that invented? When was it patented? I'm just going to give you a few numbers. Do you think it's 50 years? Less, more?
2,000 years? Like the Panther in Rome?
Not Portland cement. No, the modern cement that we're using in construction sites. So who thinks it's younger than 50 years? Who thinks it's older than 50 years? Okay. Who thinks it's 100 years? Well, it's actually going to come up with an anniversary this year. On October 21st this year, we're going to celebrate 200 years of Portland cement, patented in England by a bricklayer who was so tired of having to work with these huge white rocks that they were cutting out of a small island south of England on the coast called Portland, that he said, I'm going to invent this material and it's going to be so strong and so awesome, it's going to be this at least as good as Portland stone, and I'm going to call it Portland cement. And hence still today we call it ordinary Portland cement. So after 200 years of birthday, maybe it's time to create a new material that's even better than that. All right, and with this, let's jump in. Lucas Guest, I'll give the microphone to you. And
perfect, thank you. Can I also use that one? Or
I don't really know what works, but I'm sure we're going to.
Oh, I'll just stick with that one. That works perfectly fine. Great to see all of you. And I heard there are lots of Hertie students in here. Could you please raise your hand if you are from Hertie School? Yeah, cool, a few. And who of you is an engineer or has some technical background in natural sciences or something like that? Oh yeah, cool. So a few engineers as well. I'm glad to see. So I was asked to give a brief macro overview of cement production in general, provide some numbers, reference points that we can discuss later on in our panel discussion. And then afterwards, you will hear more about specific perspectives from research and from industry and from practice. So I want to give a brief overview in the topic of cement production and the different scales. All of you know what cement is being used for. Tobias gave a great introduction in the history of Portland cement. We need cement and concrete products for wind turbines, for bridges, for buildings in the future, probably also over the next decades until we achieve net zero emissions by 2045 or 2050 in Europe. And that's quite a short time scale. It's only 25 years compared to the 200 years of process optimization, of improving cement production facilities to make them more efficient. In a very simplified way, we can say that for Portland cement, we use limestone that is then used to produce clinker. There are lots of chemical reactions going on, high temperature process, we've heard earlier, 800 to 1000 degrees Celsius. The limestone is decomposed in carbon dioxide, which is the process-related emissions, but then we also have large quantities of carbon dioxide emissions from the fuels. And then we use clinker, between usually 60 to 90% of clinker for different cement products, and cement is not only one product, but there are several dozens of different types of cements with different chemical properties, binder functions, etc. And we'll probably hear more about those different variety of cement products later on. And then we can also use lots of supplementary cementitious materials. So other materials which, for example, blast furnace slag, which have similar properties and can be used as a clinker substitute. If we look at cement demand in Europe today, we are at around 183 million tons demanded and used every year, of which about 77% are provided with clinker. If you look at the greenhouse gas emissions from clinker production, we have the process-related carbon dioxide emissions from the chemical reactions, up to 480 kilograms per ton of clinker. And then we have, on top of that, roughly the same amount, about up to 400 kilograms of carbon dioxide per ton of clinker of the fuel-related carbon dioxide emissions. Of course, there are large differences across production sites, can be any number between 200 and slightly like more than 450 kilograms, depending on the fuel being used, on the process efficiency and the operating efficiency of the cement plant or the clinker plant. And then we have electricity, which is needed for the different grinding processes and for operating the production sites. I want to talk about these opportunities for reducing these emissions, give a brief overview of the production. But let us look at cement production globally. 200 years ago, there were probably only a few kilograms of Portland cement being produced every day. Then it increased to tons. If we look over the past decades of cement production, over the past 30 years, so since 1990, cement production has more than tripled. It's similar in a similar order of magnitude as other bulk materials like steel and aluminium. And production has now stabilized at around 4,200 million tons every year. But given the increasing demand for infrastructure in countries all over the world, demand is expected to be as high as it was previously. And this is really a striking and important number to keep in mind, that the production volumes are really of large quantity. If you look at global in-use stocks today, and that's part of an analysis we did last year and published, so you can also read the details of the analysis and the approach. We looked at different cement in-use stocks in different countries using the World Bank country classification of high, upper middle, lower middle, and low income countries. And we have like one representative example from each group. And we see that the in-use stocks in terms of cement in-use stock per capita can be ranges between 10 and more than 30 tons per capita in high-income countries, and can be as low as 1 to 7 tons per capita for lower-income countries. And as we see countries building infrastructure, roads, wind turbines, and all other forms and buildings that need concrete and cement, we probably expect an increase in the production. So the key challenge here is to accelerate the decarbonization of the production processes to provide the same material service, so a cement product with no carbon dioxide emissions. If we look at cement production in Germany, this is a map, and there are lots of statistics available from the VDZ. We have approximately 54 different production plants, some integrated production sites with the clinker production, but then also cement grinding facilities. The production volume is around 35 million tons. If you compare those 35 to the 4,200, you see it's quite significant delta. And the emissions are around 29 million tons of carbon dioxide emissions every year. There are many different policies that are currently being discussed at local, federal, European level. We heard some examples of the carbon contracts for difference earlier on today. There are also examples of hydrogen use in cement production, but there are also other international trade mechanisms like the carbon border adjustment mechanism, then the national carbon management strategy, which highlights or classifies cement and waste incineration as some of the hard-to-abate production processes. I'm sure that's something we can discuss later on as well. Then there are the national energy and climate plans, which outline the national strategies to achieve the different European emission targets over the next decades, which also only include a few words and paragraphs on industrial processes and cement production. And then there's, of course, the different reporting requirements as part of the European Corporate Sustainability Reporting Directive and the European EU taxonomy, which provides a financial framework for classifying investments into cement facilities as environmentally sustainable. If you look at the emissions figure again, we have the greenhouse gas emissions per ton of clinker-based cement, roughly in that order of magnitude. So it's around 1 ton of carbon dioxide emissions per ton of cement today, and we want to get this to net zero within the next 20 years. For electricity, we know we can use renewable electricity, and by multiplying the 100 kilowatt hours needed per ton of clinker-based cement with a quantity of cement, we end up at around 16 to 20 terawatt hours of renewable electricity to provide green cement for Germany, which is an order of magnitude of Croatia's electricity demand. We can use biomass and carbon capture and storage to mitigate the emissions from process or fuel-related emissions, and use CCS for the process-related emissions. The key challenge here, however, is to provide the infrastructure needed for carbon capture and storage, and to have sufficient amounts of renewable and sustainable biomass. And this is a really big challenge. There are also other options that are being discussed and have been discussed for the past 20 years or so. So there's a really interesting IEA technology roadmap from 2010, which already outlines the different strategies ranging from energy efficiency, so optimizing the combustion processes and thermal insulation and other measures, reducing the clinker factor, so replacing clinker with fly ash, blast furnace slag, or other materials with similar properties. But there are also novel innovations, and that's what we want to focus on in today's discussion, that might lead to zero emission cement. And one recent innovation is was recently published in a Nature paper by Cyril Dinan and his colleagues, is about cement recycling. So recycling cement as a real industrial symbiosis together with steel electric arc furnace recycling, which is an electricity-based process. So, of course, there are many other options of reducing the specific process-related emissions, for using chemical reactions and processes as part of a carbon capture and utilization reaction to permanently or temporarily store the carbon dioxide emissions. And all of these innovations might help to contribute to that new mix of cement solutions, which are low carbon and sustainable cement solutions. I want to point out one real challenge, one aspect that I want to bring to this discussion is about the carbon capture and transport infrastructure. And we, as part of an analysis, we looked at the carbon capture and storage deployment and the expected deployment in the different IEA technology roadmaps over the past decades. And here we mapped the projected carbon capture for the year 2021 from the different IEA technology roadmaps from 2010 up to the most recent one. And as you see, it follows some sort of hockey stick, but unfortunately not in the direction that we want to see it, because infrastructure deployment for CCS has really been far below the expectations. This is due to multiple reasons. The economics of carbon capture and storage did not work out. There were social protests and concerns and objections against carbon capture, et cetera, But in the end, we ended up with, or have the current capacity for both combined steel and cement production of only 1 megaton of carbon dioxide, which is significantly lower than the several gigatons those processes emit currently. So the key challenge now in the future is to accelerate this. And there are two key observations. One is that the deployment of CCS or CCTS has been slower than expected, and that we, in order to meet the 2050 targets, which is around like 2,000 megatons or 2 gigatons, which is roughly half of the emissions in those two sectors, by CCS, we need to significantly have an exponential deployment increase in those technologies. There are a few implications for the net zero transition. The first is that we need to accelerate the infrastructure deployment by better coordination and coordinated efforts. The other one is that we also need to prepare for the risk of deployment failures and have a better collaboration across the supply chain to find alternative ways, and to consider those potential supply side limitations in reporting and policies. So what happens if there's not enough demand for, or not sufficient provision for CCS infrastructure? What happens if there's limited supply of renewable electricity or biomass? And what are the mitigation strategies at a corporate level, but also on a national level, to address this potential risk? So to sum up, there are 5 points and 5 key takeaways that I want to summarize. Is first, annual cement production has increased significantly over the past decades, and we need to really find solutions to achieve net zero in the cement production quite quickly on a quite short time scale. Emissions from cement production will likely exceed with the current trends, if we don't find appropriate mitigation strategies, will likely exceed the 1.5 or 2 degrees carbon budgets. Mitigation options require additional infrastructure, and this infrastructure has not yet been deployed at scale. There are, of course, pilot plans and trials available, and that's why I'm optimistic that we might achieve the challenge of net zero cement by 2050, but it's a tough challenge. The fourth point is that there are significant efforts needed to increase the supply of those zero emission resources, renewables, electricity, biomass, and other mitigation options. And the final point is that there are innovations that exist to reduce emissions with efficiency increases, novel production routes, and novel processes that we might not know about today, but that might come into market over the next five years or so. Thank you very much, and I look forward to the discussion and especially your questions. Thank you.
Super. Vielen Dank. Ja, läuft sogar. Vielen Dank. Super. Vielen Dank, Lukas. How are we going to do this? So we're supposed to react. And let me start with a few reactions, or with a few, actually more questions towards you. And I thought this was a really good introduction, a good overview also on what we're trying to achieve here. So you lined out a lot of areas of, where we need more attention, where we need more policy push, innovation push, and so forth. Specifically, if you look at, let's say, the next 2, 3, 5 years ahead, or if you think of a legislative cycle at the European Union, specifically, what do you think would be the immediate next steps we need to do to advance on those?
Well, that's a tough question, because there's so many various levers that you can pull. I think from the demand side, of course, there are different options for changing public procurement practices to ask for higher shares of low carbon cement products, so low clinker based cement products, and those technologies and products already exist today. So if you go to any cement producer and ask for specifically more sustainable or low carbon cement alternatives, they might offer them. Of course, there is a certain cost premium, and if this sustainability premium is reflected in the design of those procurement mechanisms, I think this would create immediate market pull for more sustainable cement products, or at least slightly lower carbon. Of course, they're still far away from net zero cement. But also long-term procurement practices. For example, there's not yet a procurement mechanism for cement products bought by public stakeholders in 2030, 2040, but we will need some new buildings at that time. So there could be other market-based mechanisms to ensure that there's a certain amount of low carbon or net zero cement available, and companies could use the money today if there's some sort of clever auction mechanism, and we had different design options earlier on created by different economists to buy and procure those products. But then, of course, there are immediate opportunities for increasing efficiency at the production site level, for improving the recycling of end-of-life demolition and construction waste so that some of it can be reused. And then, of course, it's about using as many clinker substitutes as possible. There are lots of slag heaps and not used cementitious products that could be put on the market and used in cement products to improve the quality. But then, of course, the big elephant in the room is material demand reduction and clever, better design options, because we can save lots of the cement being used by doing better static analysis. And sometimes there's several studies from a former research group that some of the cement in buildings is not being used as efficiently as possible. So we could immediately reduce cement demand by, let's say, for some new buildings by 20%, of course, under certain assumptions, etc., at slightly higher cost as well, because we need to commission new studies and analysis for these static analysis, but this could immediately reduce cement demand, and there are other design options that could be pursued. So this would be a bunch of flowers, so to speak, of options to go for.
That's a beautiful bouquet. I mean, I think that you're definitely pointing in a good direction. Thank you for that. Any other reactions, follow-on questions, immediate responses to Luca's presentation?
No, well, I would say from the corporate perspective, it was a very good overall picture that there is no one cure-all. So we have to work on all the levers, and from the corporate perspective, I will show you later on in my presentation, we are working on all that. And I think we have to deal with lots of uncertainties, but what does it mean? This means that both for policymakers and for companies, we have to take bold actions. We need clear targets, which we have as a company, and also as a sector. We have sector targets. We have a global association of the cement producers. We have a European one. We have the VDZ, which is also present in the room today. And these roadmaps mean a clear commitment. And this commitment is to get to net zero by 2050, or even in the EU by 45. And this is what we are working on, and I'm happy to show you later on what that means from the perspective of a global company as Heidelberg Materials is.
Do you have a reaction on what was said? Any reflections from your perspective?
Yes, I think there are many potential approaches to reduce the CO2, but a big problem is that we are running out of time. So we don't have develop a new product which is flowing CO2, then you have to face the legal improvement of the product, and this takes too much time, and at least in Germany. And yeah, this might be one problem in the future. There are many ideas, but to come from the lab to the market, this takes a long time.
This is a very important point. I remember the last session that we had on the funding side, which was very, very interesting. And also, I will make that point later on, that funding is really crucial to get that transformation done. And we need huge funding to bridge the gap until green is the new standard, because that's where we're going. It's not only about these products becoming more expensive, but the gray ones will become more expensive. And this is the ambition of, for example, at least in Europe, of the EU emissions trading system. That's what we're all hoping for, and we need these price signals. But funding is only one part of the story, but it's also about accelerating things. You can't do it with business as usual. For example, maybe I can show a little film later on. We have one full-scale CCS project, carbon capture and storage project, kicked it off last year in Germany, in Geseke, North Rhine-Westphalia. And we were able to do it because we were bold and brave in that respect and take risks as an early mover, but at the same time get the funding from the EU Innovation Fund. And it needs these kinds of decisions to get started, because there is no plan. We have to do it step by step. And it's not only us as the emitters who have to act, but we have to create infrastructures. We need a whole building ecosystem to change. It's not only, for example, we can, in our sphere of influence, it's how to produce cement, what can we do, how to produce concrete, what can we offer to the market. But in the end, the whole construction ecosystem needs to change. Because, for example, if you produce, to put it very, I'm not an engineer either.
But let's leave some for the debate for later. I wanted to open up also a little bit to the audience in terms of reaction. So Niels asked me to be very strict on time. Now, I can be very strict on time. I'm not going to be super strict on time, but let's maybe agree that we don't exceed a minute or so in our answers, so we really keep a lively debate. I think that's super important. Let's open up quickly to the audience on the introductory keynote from Lukas Gast. Any reactions, any questions on that before we continue with more questions here on the panel? Yeah, there's a hand.
Yeah. I'll do it without mic and it'll be super loud. Yeah, it's not. Thanks for the input, first of all. It's not precisely a question, it's more like an area of interest that I'd like to hear more from your industry insights and expert perspective, which is regarding the recycling of the cement, because this was the first thing that struck me, and I'm actually not educated on that at all. So that would be really great if maybe, especially from R&D perspective, you could pick up that point now or later on and give us some more insights.
Yeah, no, that's a really good point. Let's collect some of these and then we'll see when we get to them. Any other thoughts or questions from the audience?
It's a question in a slightly different direction, actually. I wanted to know how important actually public perception is and the awareness of the transition to improve processes, and how we can improve this awareness.
The awareness of in society or among stakeholders in the
among both, but mostly society, actually, I think.
Very important. I think there's one third hand in the European hand.
Yeah, my question is a bit regarding these alternative processes that are already out there. For example, I read something about this process of producing cement at very low temperature comparatively to what's produced now. How much do you know about these processes? How much of that is valid? How much is maybe bogus? Yeah.
Very good. I think we're gonna we're gonna collect these questions. I think I'll let Lukas respond to the ones that are relevant to him, but I think we have a superstar panel here that will definitely get to your questions. So it's great to see where you're interested in, and you're pointing, I think, to the exact right directions. Lukas, do you want to give one answer to those questions? And you don't need to cover everything.
Yeah, exactly. I can come back to those points later as we discuss them. I think the point with like social perception is really important as well, because it's also about consumer behavior, people building a house, their own house, who probably cannot really buy like net zero cement products at the market at the moment. And of course, there's a higher cost premium that has to be paid. But I'm not an expert in that topic, but we can come back to that later, about the new innovations and technologies that might be available. It already also depends on technology readiness is one side, but then we also have the scale of current production. And to my knowledge, these processes operate at pilot level scale, but not yet at full commercial scale. And this is exactly what Carolin mentioned earlier, that we need to scale up those processes rapidly. And for that, we have to mitigate the uncertainty around the infrastructure policies, but also have to be innovative and really take a step forward.
All right, with that, let me hand over to Carolin Boßmeyer for a little keynote. As a background, and I think many of you are aware, of course, Heidelberg Materials has been around for a long time. It's one of the biggest companies we have on the German stock market. I think if I got the numbers right, there's 55,000 employees working with Heidelberg Materials.
51.
51,000, okay. More than 50,000 people working with Heidelberg Materials worldwide. So it's a huge corporation, and so and we're so glad you're here to take the time, because it's so easy to talk theoretically, let's decarbonize, and it's hard, but it's still relatively easy to stand in a lab and say, I got this, and then to actually do it on a global scale. So yeah, we're very, very interested to hear your presentation. Carolin, thank you.
Yes, thank you very much for having me. I can't see the presentation on the screen. Yes, so I will walk you through the main challenges and levers from a corporate perspective, and you will hear about some things that Lucas also mentioned, which is good. So who are we? You just started to talk about that. We are one of the largest building materials companies globally, a DAX 40 company. With a long history. We turned 150 years old and last year, and you can see on that picture our CEO Dominic van Achten on the right-hand side. So it's around 51,000 employees working for the whole group, and it's a very regional business. This is important in many respects. Also for our group decarbonization targets, as the framework conditions really vary a lot from country to country. So please keep in mind, we are talking from a global perspective here and finding global solutions. It's about 3,000 sites on 5 continents, and Heidelberg Materials is vertically integrated along the value chain with leading positions in aggregate. So we are operating extraction sites worldwide, and in cement and ready-mix concrete, and we are also running an asphalt business and a trading business. So it was mentioned before, concrete is indeed indispensable for fulfilling the construction tasks of the future. It is the second most used material in the world after water, and this is because of its good properties and the range of applications, etc. And it comes with a number of advantages, and it is extremely versatile, like locally produced and sold. It's recyclable 100%. It's durable, sound absorbent, etc., etc. And this is why you can do great things with concrete. Look at this architecture, for example, or this one. This is a structure of the Mose project that prevents Venice from flooding, for example, or a 3D printed house, as you can see at this picture. But as you know, and this is why we are sitting here, this all comes with a very, very heavy energy and CO2 backpack, and we have to find solutions for it, especially as we know that we will continue to need huge volumes of concrete and cement in the future as well. Originally, I wanted to have a small stop over here because my experience is that very often cement and concrete are mixed up. Lucas explained it a bit. Also, and it's important to understand some of the basics, because only then can you understand where the levers lie for climate-friendly cement production. And what is important is to see that the CO2-intensive part of the production is the cement clinker production. And then also the content of that CO2-intensive product in cement and then in concrete. So you have, as a raw material, you have limestone or clay or a mixture of them like marls, and they're needed as a source for calcium carbonate. You need that for the binding function of the material. And then you need very, very high temperatures to produce an intermediate product out of that, that is cement clinker. With a temperature of 1,450 degrees heating. You can see the gray nodules there, that is the cement clinker on the second picture. The cement then is the gray powder that you may know. It's an hydraulic binder. That means that it's a finely ground inorganic material that sets and hardens if you mix it with water. So you can say the cement then is the glue in the concrete later on, and concrete is what you can see in your environment. It's a kind of artificial stone, and this is produced when you mix that cement and water with aggregates, that is sand, gravel, or even recycled material and water. This is what Lucas also mentioned. I will repeat it again because it's very important to understand that there are two sources for CO2 emissions from clinker manufacturing that need to be tackled with a range of measures and technologies. The majority of the emissions comes from the so-called calcination of the limestone. You can see the chemical equation on the left, and this is an unavoidable CO2 coming from the process. It's accounting for 2/3 of the CO2 emissions, and the rest, you mentioned it as well, Lucas, is fuel-related emissions that can be addressed by a fuel switch. So if you manage to run the process with renewables, carbon-neutral fuels or electricity, this side of the problem is solved. We have, as a company, the most ambitious CO2 target for 2030 for the direct emissions from cement production, the so-called Scope 1 emissions in the sector, and we are striving for a reduction of about 47% compared to 1990 by 2030. And we want to achieve this by a mix of measures. You can see the corresponding 2030 targets on the right-hand side. At the clinker level, we need more alternative fuels and biomass to replace fossil fuels, to replace like coal and oil. And the second lever, which is a very powerful one, is reducing the amount of clinker in cement, the so-called clinker to cement ratio. And please keep in mind, you can see a number there, 68%. We want to get there by 2030. This is a global target across all countries and installations and markets of a huge company. And of course, single types of cements can have a significantly lower clinker factor. And the third lever is that we are also now introducing, as a front runner in that field, carbon capture and storage or carbon capture technologies. And we will have implemented first projects by 2030. We also have, I will not go deeper into that, but we also have targets, you need targets as a company, that's the driving force. And we also have targets for all 3 scopes to the greenhouse gas protocol. And these targets have also been validated by the Science Based Targets Initiative, so they are aligned with the 1.5-degree framework of the SBTi. And given that, it's our ambition and our goal, and that's what we promise to our investors and to the market, that we want to achieve net zero in line with the SBTi by 2050 at the latest. So avoidance of CO2, that's an important message, has priority. That also makes sense, not only from an environmental or climate point of view, but also from a business perspective. This is why we are constantly working on low carbon products. And what does that mean now in terms of levers and measures? The first point is energy. I mentioned that before. We are maximizing the proportion of waste-based alternative fuels, including biomass, to replace fossil fuels. It means improving processes and investing in plant efficiency. It means increasing renewable energy and waste heat recovery. And we're also working on, this was mentioned, I think, in the previous panel as well, we're working on electrification of our processes and also explore the potential of electrifying the calcination or the whole process, and also exploring the use of hydrogen. But this is not state of the art in cement production nowadays. Then the important thing of the clinker to cement ratio, so reducing the proportion of clinker in cement and then also of cement in clinker. We are, to this end, we are developing cements and cementitious materials containing less clinker, also alternative binders to the Portland cement, and concretes with a lower cement content. And that means that we that we need alternative raw materials, the so-called secondary cementitious materials that are needed to take over the function of clinker in cement. And these SCMs can be have a huge diversity. They are natural materials or industrial byproducts that exhibit cementitious behaviors when combined either with water or other compounds. And therefore, we need to strengthen our portfolio of these SCMs, so the byproducts or waste of other industry like fly ash or blast furnace slag. They're coming from the steel sector or the coal sector. I'm coming back to that point later on. But it's also natural materials like natural pozzolans or calcine clays. We will not be able to explain the technicality behind that today, but just saying they have a very different origin, and they're also, and this is important because we have there the link there to circularity, it's also construction and demolition waste that we can use. And so the third point is innovative circularity technologies. So demolition concrete can be fully reused in fresh concrete with advanced recycling technology. And this is why we are investing heavily in these kind of advanced recycling, because there are lots of benefits coming with it. For example, in forced carbonation, you can incorporate that the reverse chemical equation we'd seen before. You can incorporate CO2 in concrete. This is happening naturally anyhow, but you can enforce that process. So you can use building materials as a CO2 sink. And in the long run, there is a carbon removal potential to take carbon back from the atmosphere, from biomass, if CO2 is from the atmosphere or from biogenic resources. So this was an abstract description of some of the important levers to decarbonize cement, but they have to be put into practice, and that needs to be done project by project and day by day and side by side. And walking the talk means really investing in manifold activities. I've picked out some here. I won't read them out now, but we can leave them for this discussion later on. It's about investments in countries, for example, in grinding facilities, so that you can deal with a variety of material that we now want to use. It's about huge R&D project. We have a huge global R&D term, really looking into all the technologies that are available on the markets and checking them. And it's also about acquisitions of companies to get access to material that can replace the ordinary Portland cement. And to make a long story short, there is no thing such thing as a silver bullet. So we need to tackle a broad range of steps, innovate. We need innovative spirit and technologies, and that is what we are doing as a company. It means pursuing a clear goal while dealing with a lot of uncertainties as well and path dependencies. And what I would really like to stress is that scalability is key. We need to pull many levers on the one hand side, but also identify scalable solutions that go beyond niche applications and that can really, make a difference. For example, where's that one now? I had some here. Sorry for that. That means, I'm repeating a little bit what it means in terms of scalability. We need the access to the alternative raw materials. So sufficient availability is really maybe a bottleneck, and it is crucial to substitute the materials. It's also about things like building codes and standards, product standards in the company. They need to be adapted and to be further developed to gain flexibility and speed up implementation. Things can't stay as they are. We need to be dynamic in, everywhere in society and also in policy making. And the customers, they also need to be convinced. We need market acceptance. We need the public sector to support this by public procurement. And we have to take into consideration that we need various solutions due to the differences from country to country. But in the end, also there are remaining technical challenges and limits for applying new types of cement and concrete when it comes to the The building must not fall apart. The bridge must not fall apart. So durability, strength, exposure classes, workability of concretes, this is all things we have to take into consideration. So the technological ambitions and measures, as well as the targets in the area of climate protection and circular economy, they are also, of course, reflected on our product strategy. It is that simple. We have to earn money. And in the end, what matters is that we need to accelerate the market ramp up for these low carbon and circular products. And it's a step-by-step path with intermediate goals. What you can see here is that our customers benefit globally from more sustainable products and solutions already today. And this portfolio is being expanded now, day by day. You can see the light green, in the light green, this is, for example, reduction of CO2. You can see products with a footprint of minus 80%, for example, compared to conventional products. And you can see products that are really up to 100% circular, for example. This is all possible already today. And in January this year, we have decided to launch a new global brand to push for that, and a brand for low carbon and circular products to bring them to the market, offer them to the customers, and to harmonize the sustainability product portfolio on a global level. This is called EvoBuild, and the products there are either low carbon cement and concrete or circular, or they feature a combination of both, and we have clear criteria that have to be met to qualify for being an EvoBuild product. The other cement companies in the world have that, of course, as well, these kinds of product strategy. That's not something that only we are doing, of course. And our commitment as Heidelberg Materials is to generate half of our revenue from these products by 2030. And then we are taking the next step and try to see what will be the ambition. And now, as the last point here from my presentation, is turning to the role of CCS and CCU. So the implementation of industrial scale carbon capture and utilization and storage project is a key element on our journey to net zero, or to be more precise, we need it as a hard-to-abate sector with process emissions, and only then can we offer net zero cement and concrete. And this is widely accepted. It's also reflected in the strategies of the EU and the strategies elsewhere in the world, or in the carbon management strategy of Germany, or the green lead market strategy of Germany. That is accepted, and we have pledged to cut CO2 emissions already by 10 million tons cumulatively by 2030 with several projects, and our ambition is and strategic approach is to create a large portfolio and scale that up fast. We have an outstanding lighthouse project gaining attention around the world, which is happening in Brevik in Norway. Here we are implementing the first industrial scale carbon capture and storage project at a cement plant, and mechanical completion is scheduled for end of this year. And then it's designed to capture half of the plant's CO2 emissions, that is 400,000 tons annually. And this was visited last year in January also by our German Vice Chancellor and Minister for the Economy and Climate Action, Robert Habeck, with a very, very huge delegation from Germany. And that was really a decisive step towards preparing also carbon management strategy for Germany, and also to take the responsibility as the largest industrial player in Europe and the third largest industrial nation in the world. And in addition, just as a side note, in addition to our EvoBuild brand, we have also launched another new brand, which is called EvoZero, and which was developed specifically for Heidelberg Materials future CCS-based net zero products. And the first net zero achieves EvoZero achieves its net zero attribute through the application of CCS technology in Brevik. So these technologies and the implementation of projects, they are very demanding. It's a real pioneering work, but we have to start. I mean, we just have to start and to do it. And we are starting in Europe and North America, as you can see here. That's a project portfolio. And every project is really unique as regards technology, size, infrastructure, and partners. So carbon management means really completely new infrastructure, completely new value chains, partnerships, business cases, completely new facilities are being built at the cement sites. Our task as a cement producer is to prevent the CO2 from being released in the atmosphere. But to this end, we have to cooperate with partners, with plant manufacturers, operators of future pipelines for CO2, storage facilities. The ports will play an important role as well, and CO2 hubs, clusters will emerge. And given the amounts that is what Lucas also mentioned before, given the amount of CO2 we are talking about, and that also the politics is talking about in their scenarios. We know the scenarios for the CO2 from various sectors. Pipelines will be crucial. And source to sink by pipeline is key for efficiency and cost efficiency, etc. Of course, also other transport modes will contribute, like ship and rail. So all players in the value chain must work together, and in the end it will be our task. We have to decarbonize all the remaining clinker plants that we are having. So we all have to move in parallel, and it will only work with a clear political commitment. This is clear, and this is why we are appreciating that now things are really getting moved, like the carbon management strategy in Germany, the carbon management strategy at the EU level, and also the Net Zero Industry Act targeting the manufacturing of clean technologies in Europe. So policy making is really now in a decisive phase for setting the course. And this is, what is needed. My last slide, what is needed from politics, it's really that we get that strategies and a clear path forward, including CCS and CCU, that we manage to get the legislative framework for capturing, transport and storage being set up. It's not done in Germany, it's just now being negotiated in the parliament, but has been adopted by the cabinet, to put it simple. We need push instruments like effective funding programs, including the CCFDs. We learned more about this in the morning. We need pull instruments. They're equally important, like green lead market, to unleash the demand for these products. And we will also learn that this might be a very cheap way of supporting the markets and this transformation of industry. Storage of the infrastructure is key. Lucas mentioned that before. And we have to facilitate energy-intensive industries or facilitate the access and ample supply of renewable and low-carbon electricity, because we will need more electricity also for the capturing part. And planning and investment security, I mentioned that before, and acceleration of planning and approval and social acceptance. Social acceptance, it's the last thing here on that slide, but it's very, very relevant in our projects that we are establishing here, implementing here, for example, in Germany. For example, under the EU Innovation Fund, this knowledge sharing and stakeholder management and social acceptance is a very crucial part of the projects. So thank you very much.
All right. Carolin, Boßmeyer, thank you. That was a long tour and ride through the decarbonization path of a large corporate, and I think very, very important. Also shows the many challenges along the way. It does leave me on a positive note, though. It feels like, yes, it's hard to abate, but it's possible to abate. So maybe that's one takeaway. The other thing, and I think you know, that was halfway through your presentation, and I think it's one of the key takeaways I want everyone also to walk away with here today is, it's not one technology. There's a proliferation of green cement technologies, whether it's on the materials side, the energy side, or the application side, even the design and construction side. And I think that's super important in a policy context, because policymakers, and I mean, you can do that test, ask 100 policymakers in Berlin or Brussels, how do we decarbonize cement? And 99 will say CCS. Because people are always looking for a single silver bullet. It's just how politics has been done for the last few hundred years. And I think it's crucial for everyone's cost, speed, and the health of this planet, we need to come to a thinking of many technologies at the same time. There is not one winner takes all. We know it from renewables. We have all kinds of renewable sources in all kinds of places that are now connected through all kinds of battery storage systems to stabilize the grid and so forth. Well, guess what? It's the same on these other, tech verticals, on our mission verticals. We need a lot of solutions. And it's actually one thing I wanted to also just to underscore this point. Bellona is one of the leading environmental and climate advocacy groups in Europe that is very much in the depths of cement and other industry processes. And so when they looked at CCS and how does it actually work, actually very much looking at the Norway plant, the Breivik plant, which is an amazing, technological progress. It's a plant that's more than 100 years old. So it's a really old cement plant with all the emissions that you can have in there. And of course, there has been optimization, but it's an existing plant. This is old capital. In order to take the CO2 out of the process, you have to install a 50-meter absorber on top of it. Just imagine that structure on top of a chimney and factory, a 50-meter high absorber is so much CO2 coming out of the system. You need a 50-meter high thing. It's running on an amine wash, which is an old existing technology, so there's very little rocket science in that thing. It's optimized, it's modern, it's as good as it gets in amine, but it's a chemically intense process. So again, not the perfect in the long run, but that's as good as it gets at this scale today. Then all the CO2 is captured in what? Well, it needs to be put into something to move underground. It needs to move first in a storage tank, right? Because that CO2 needs to be shipped actually to the sink side. Well, but the boat only goes just like ferries, every few days or hours, or I don't know the frequency, but the boat is not going continuously, but the factory is going continuously. That means you need huge storage tanks of that CO2 to store it where you can load the ship. But in order to store the CO2, you cannot store that much gas in an open space, so you need to compress it. So you need, again, lots of energy to compress the gas into a liquid form, just like liquid natural gas, but here in this case it's liquid CO2, into the huge pressure tanks. But for tanks to hold that much pressure and that much CO2, they weigh what, like what was the number? Like 25,000 tons or something per tank?
I don't have the size there. I know that
I was looking it up on the Breivik website. Anyway, what I'm trying to say is huge steel tanks, huge embedded emissions. Again, as good as it gets, we got to start somewhere. But like you're getting an idea of why this is so far from where we actually want to be, 10 or 15 or 20 years from now, and certainly by 2050, we need to do this much, much, much better in terms of lower emissions, embedded emissions. Then that ship needs to go from, that side is near Oslo, but the sink side is near Bergen. That's a 600-kilometer sea journey in the open sea. And then again, it needs to be unloaded, put in another pressure container, and then finally it gets pressed underground through an underground pipe that's sinking it into the sea. Under the seabed, I'm not questioning the topology of that. I trust that the geologists have, that's fine. But just think of the engineering that goes into all of this, the materials that go into all of this, and the cost to go into all of this. And then this is only enough for half of the plant's emission. So it's an amazing pilot. It's a gigantic pilot. This thing cost, what, like 300 million just on the plant side, right? And then twice that much on the sink side. If you compare that to all the CO2 emissions from cement just of Germany, that's 80 times more. So if you do
That's why we have a super intensive to reduce CO2 as good as we can before coming to these kinds of technologies. And you also, it's completely true what you're saying, but it is the very, very first industrial scale product in the cement sector. Yeah. So it's visited by people from all over the world to have a look at it. And that's tough, of course. We're talking about a complete transformation of a production process.
Yeah, and so I guess where I'm trying to go with this is a part of the big numbers and the back of the envelope, right? So if we would use this technology today, which we shouldn't, we'll probably end up somewhere between 20 or 30 billion just for German cement emissions per year, you know, in the construction. That's without the operating. So clearly, as an economist, I'd say, well, why don't we use that as a benchmark? It's hard to imagine that we find a different process that's more expensive than that. And I think with that, actually, I wanted to hand over on the R&D side, because I think if that's our price tag, so installing CCS for Germany, just installing, not the operating, would be, if we use the Norwegian numbers, very rough calculation, 25 billion. What can we do on the materials side to cut that cost?
25 billion?
Yeah.
That won't be the price when we
Hopefully
scale it
not.
up. No, hopefully not. Then we wouldn't do it. Wouldn't be doable. No, no.
Okay. Okay, hello everyone. Warm welcome. First of all, thanks for you and Johanna for inviting me for this talk. It's a great pleasure to be here. I'm working for the Fraunhofer Institute, which is Europe's largest research organization. We have now also about 30,000 employees worldwide. And I'm working in the Department for Inorganic Materials and Recycling in the Institute for Building Physics, located south of Munich. I would like to present you today a few new approaches, some funny ideas, what we can do to reduce the CO2 amount in building products. I'll show you some new materials, some technical perspectives, and the so-called pyrocarbon cycle. And with that, I would like to start with the carbon cycle. So the carbon or carbon dioxide cycle is basically consists of three partial cycles. This is all known. You have, if you look at the partial cycle of in the atmosphere, if you look at on a tree consumes CO2 during lifetime, and after end of life, it decomposes and leaves the CO2 again to the atmosphere. So it's a tree in itself is a climate neutral living. Plants can assimilate CO2 by photosynthesis, animals eat plants, and so on. This is a cycle in itself. You also have a water cycle. This is quite similar. And here is the important thing. We have also water plants and algae or bacteria, which can produce carbonates. So they can produce really a carbon sink in the ocean. And at least we have a third cycle, the land cycle, where we have dead organic material, which can be converted into peat, coal, crude oil, or methane. So we have another carbon sink in nature. And all these cycles are combined with each other. And now came the humans and had the idea to use these carbon sinks as fossil fuels. And this is one reason why we release CO2 into the atmosphere. And the cement industry needs the carbonates for cement production. So these are the two processes which increases the CO2 content in the atmosphere. And so why not trying to convert these arrows? Maybe it's possible to create or build carbonates, or even can we build or generate coal? And this would be two climate positive processes which would reduce the CO2 amount in the carbon cycle. We always have to look at a cycle, not on just one single step. And therefore, I would like to ask a question. What do you think, how many tons of CO2 you have to remove from the atmosphere to efficiently remove 1 ton of CO2? Sounds silly. In that, you have to remove the double amount. So you have to remove 2 tons of CO2 to efficiently remove 1 ton of CO2, because the atmosphere is in connection with the water cycle. So if you remove 1 ton of CO2 from the atmosphere, half of the amount of CO2 will be released from the water to the atmosphere. So this makes the things even more complicated. But let's go to the first idea. Is it possible to generate biological building materials? Yes, it is. There's a big project running from the NASA called Biomason, and they've spent unbelievable $50 million to investigate whether it's possible to generate building products on Moon or on the planet Mars, because it's economically not viable to transport concrete from Earth to Mars. And the idea is to mix the sand, which is available on Moon or Mars, together with human urine, so it's a little bit ugly, and put some algae to it. And then they start to run their metabolism, and then they can create calcium carbonate. And you see a few products. It's a so-called regolite stone. Of course, the production is not highly productive, but it's the first step. And we have now a project together with our colleagues from Fraunhofer FEP, and we try to use alternative materials, let's say, for example, waste concrete as a starting material. And the metabolism of these cyanobacteria is very slow. They're one of the oldest living animals on planet Earth. They are here since 3.7 billion years. They're one of the first animals on land, and they can produce biocalcite, so they can fixate CO2 from atmosphere in the formation of calcite, but they need, for 1 centimeter thick plate, about 30 years, so this is very slow. But finally, the colleagues from FEP, they found a method to accelerate the metabolism of these cyanobacteria. So, and then of course we want to upscale this process, and this is a running project, and we hope to get some good results maybe in 1 or 2 years from now. Here's one of my favorite slides. It's about concrete recycling. The problem in concrete recycling is if you use mechanical methods like a jaw crusher or an impact crusher, you reduce the mechanical strength of the gravel. So by overcoming the compressive strength, you increase microcracks in the gravel, and this reduces the mechanical strength. So if you use then these secondary aggregates in fresh concrete, you will never reach the same strength like in original concrete. So if you use mechanical methods for concrete, it's a typical downcycling process. But there's an alternative. It's a so-called electrodynamic fragmentation technique. We put the concrete underwater between 2 electrodes, and we apply a high electrical field in the range of 200,000 volts. And then immediately we call it streamers, some lightning discharges run through your composite material along phase boundaries. This leads to a mechanical weakening of your product. And the first lightning strike, which reaches the counter electrode, generates a plasma channel. This is spreading very rapidly. It generates a pressure of up to 10 gigapascal, which is in the range of a TNT explosion. And then you can tear apart the concrete. And this is the only technique which only has to overcome the tensile strength and not the compressive strength. And the good news is we are obtaining 3 different fractions. We obtain a coarse fraction bigger than 4 millimeters, and this is now completely free of cement stone, and this has the same quality like the original aggregate. Another fraction is a mixing of sand and carbonated cement stone, and most interestingly for us is the filter cake, because this contains secondary calcite and amorphous silicates. So the effect is that the lightning strike releases the calcium ions in the process water. The water becomes highly alkaline, and this absorbs CO2 from atmosphere like let's say like a vacuum cleaner. And so in every case, the cement stone was completely carbonated afterwards. And now we can use this filter cake, which you see here on the right-hand side. We have to adapt it a little bit by chemical means, and then we can really produce again an ordinary Portland cement out of these filter cake fractions. And if the whole cement industry in Germany would use secondary calcite or biological calcite for cement production, we could reduce theoretically 2/3 of the CO2 emissions. At the moment, we are upscaling this technology it's still a long step. These slides are already unbelievable 25 years old. But in last 4 or 5 years, we have found an industry partner who can build generators, which makes it now economically viable. So now we are in the range of an energy consumption of 2.3 kilowatt hours per ton. And we now try to upscale it to about 10 tons per hour. This is a technique. So it is possible to recycle concrete really 100% with this technique. And we had also many projects with this technology. Coming to a material, Lucas and Carolin mentioned, cement is mixed with so-called supplementary cementitious materials. In Germany, usually we use a fly ash or blast furnace slag. But the problem is in 2030, when the coal power plants will shut down, we have a lack on fly ash. So we will miss 2 million tons of fly ash. And when the steel industry will change to hydrogen technology, we'll also have a lack of about 8 million tons of blast furnace slag. And if the cement industry wants to reduce the clinker content down to 50%, we need about, in Germany, about 16 billion tons of supplementary cementitious materials in about 6 years from now. So it's a big challenge. The only material which can fill this slag are clays. Clays are always available worldwide. So the whole cement industry would need about 400 million tons of clays annually to fill this gap. And here's one example of a clinker-reduced cement, a so-called LC3 formulation. This stands for limestone, calcined clay, and it's a 3-component system. It's a formulation which contains only 50% of cement, clinker, 30% of this calcined clay, 15% of limestone. And this gives you a concrete with the same properties as if it would be made from 100% of cement. Calcined clays, you can treat clays. There's not just only one type, there's many types of clays. One type of clay can be treated by thermal means. Other ones, they need more mechanical grinding, mechanochemical grinding. And we have now a working group which investigates which clay has to be treated in which way to become a supplementary cementitious material. And we can also use soil excavation. Soil excavation contains lots of clays. This is in Germany the largest mineralic waste stream with about 125 million tons annually. And we try now to find methods or technologies to separate the clay from the other fraction of the soil excavation and then convert it into a supplementary cementitious material. Coming to the other idea, the formation of biological calcite is it's more or less a carbon capture strategy. Now I want to present you a technology which avoids the formation or the generation of CO2. This is called pyrolysis, and this is a method which produces pyrochar or carbonizates. If you have an organic waste like biomass, car tires, methane, plastics, and so on, and you apply a combustion, you convert every more or less carbon atom into a CO2 molecule. If you use a pyrolysis technology which works without oxygen, you get other products. You get a so-called biogas or synthesis gas, which contains hydrogen and carbon monoxide. Depending on the raw material, you get a highly valuable oil. And the mineralic waste is combined with the carbonizate. So, and these products you can reuse again. And for example, if you use biomass after pyrolysis, you can remove about 40% of the carbon as a carbonizate, and you avoid the generation of CO2. So this is clearly a climate positive technology. And now the big idea is to use this pyrochar or these carbonizates into building materials, which you see here. Here were our first trials with mortar, and on the right-hand side, we used concrete and added pyrochar to the concrete. And take these numbers, 1 part of pyrochar reduces 3 parts of CO2 in your building material. And the first idea was to use this pyrochar just as an additive. And there were some challenges. You can't just throw in pyrochar to concrete, it will swim at the surface. But we have some tricks. We have also now a patent to modify this pyrochar so that they can mix it together with concrete. But we wanted to go a step further. We found a method to granulate this pyrochar. So now we can get a particle size distribution. And here you see, for example, the approach. We replace the sand fraction smaller than 2 millimeters by this granulated pyrochar, and it still works. So the concrete has the same properties, mechanical properties. We were also surprised, but it's lighter than normal concrete, because if you replace gravel, quartz by pyrochar, it's much lighter. And I think it's even much prettier than the normal concrete. So, yes, we're still not at the end of the road here. I think there's still some open questions. Maybe we can even in future replace big gravel by this pyrochar granulates. On my last slide, I want to go back many thousand years. Let's ask the question, which properties should a perfect concrete possess? Ideally, it should contain no cement at all. Then it would be low, it would have a low CO2 footprint. It should be suitable for construction. It should be sustainable. Maybe if you use, for example, if you can use locally available resources. Should be recyclable. Should be durable. And a nice add-on would even be if it would possess some earthquake resilient properties. Now you would say this is many wishes at once. Such a concrete isn't possible. The answer is it was possible. Here you see the Pantheon from Rome. This is a concrete dome. Has been built in the 2nd century after Christ. So it's almost 2,000 years old, survived 7 earthquakes without any crack. Problem is, we still don't know exactly what the Romans did at that time, but we have another project together with the Max Planck Association to solve this riddle. I think we are on a good way. We have now, I think we now know which cement system the Romans used, but in 2 years from now, I think I can show you the answer to this question. And therefore, thank you for your attention. Exactly.
Fantastic. Dr. Volker Thome, vielen Dank. Thank you so much. So now each of you is qualified for a PhD in cement materials. No, I mean, thank you really for sticking with us and also trying to, get around this complexity. I know this Hertie is not an engineering school, so even more so appreciated, that you're really caring and also trying to understand the different levers.